when some wag said it's feasible to think responsibly about one thing and not the other. Well, I could see from that one sentence that that was perfectly ridiculous. And it pushed me further into my natural drift, which was into learning all the big ideas and all the big disciplines.
Welcome to the deep dive. Just take a second and look around you. Seriously. Your phone, maybe the building you're in, that traffic light you just passed. You are absolutely surrounded by engineered stuff.
All the time, yeah.
But, how often do we really stop and think about the core ideas, the principles that actually make all that possible? We're talking like tiny microchips to massive skyscrapers.
It's kind of invisible, isn't it? The thinking behind it all.
Exactly. So today, we're going deeper than just admiring the gadgets. We're doing a deep dive into what we're calling the big ideas in engineering. And look, this isn't going to be a history lesson listing inventions or some dry textbook thing.
No, definitely not.
It's about finding those common threads, the unifying concepts that cut across all the different fields: civil, mechanical, electrical, chemical, even software. It's about the engineering mindset.
Yeah, what's fascinating here is how these core ideas really tie everything together despite how different the fields seem. Our goal today really is to give you a shortcut, a way to feel, well-informed about how engineers tackle problems, how they come up with these amazing solutions we use every day.
And maybe take for granted sometimes.
Often take for granted, yeah. We've dug through our sources, pulled out the really important nuggets, and honestly, I think you'll find some surprising stuff, maybe have a few aha moments. It might just change how you see the world around you. You start seeing the engineering everywhere.
I love that. So, yeah, settle in. We're going to unpack some really fundamental concepts, things like systems thinking, the whole balancing act of optimization and trade-offs,
Crucial stuff.
elegance of feedback control, the rise of automation, materials science, that's huge sustainable energy, obviously, and maybe surprisingly, learning from failure.
Oh, absolutely. Failure is key.
And you'll see how they all connect, how interdisciplinary it all is. By the end of this, you should have a totally new appreciation for the engineering behind, well, everything. Not just what engineers build, but how they think to make it happen. Okay, let's get started. Hashtag tag check take eco. Systems thinking and the interdisciplinary approach. Okay, let's unpack this first big idea. Systems thinking. When you think about massive projects like building a global shipping network or launching a satellite or even just designing a modern city's infrastructure, it just seems impossibly complicated.
Totally overwhelming sometimes, yeah.
How do engineers even start to manage all those different parts, all those experts from different fields? And what happens if they don't think systemically, if they just stay in their silos?
That's such a critical question because it gets right to the heart of maybe the most important shift in modern engineering thinking. Systems thinking. Basically, it means you don't look at an engineering problem as just a bunch of separate bits and pieces.
Like designing an engine over here and the electronics over there.
Exactly. Instead, you see it as an interconnected system. Everything affects everything else. Our sources put it nicely, integrating multiple components and disciplines into a coherent whole. And this isn't just like a nice idea, it's actually formalized now. There's a whole field called systems engineering.
Right, so it's not just hoping the mechanical guy and the electrical gal and the software team all magically sync up at the end. What goes wrong when that doesn't happen?
Well, that's exactly it, the silo approach. It often leads to problems not with the individual parts, but with how they interact. You could have a perfectly designed engine, but if the control software isn't integrated right, the whole car fails. Or a super strong bridge that causes massive traffic jams because nobody thought about flow.
Ah, okay.
So systems engineering is specifically focused on how you design, integrate, and manage these really complex systems across their entire life. From the first idea, figuring out requirements, through design, building it, operating it, even thinking about how to retire it eventually.
The whole life cycle.
The whole thing. Its main job is making sure all the pieces, structural, electrical, software, how people interact with it, environmental stuff, cost, everything gets considered together as a whole. It's absolutely vital for any big, complex project where different subsystems just have to work together smoothly. Without it, you get parts that don't talk to each other, or worse, they conflict. Leads to delays, costs go up, sometimes things fail badly.
Okay, so give us some solid examples. Where is this systems thinking absolutely essential? Like, where would things fall apart without it?
Okay, think about a modern car. Perfect example. It's way more than just mechanics now, right? You've got the mechanical stuff engine, transmission, chassis from mechanical engineers.
Sure.
But then there's this huge layer of electrical systems, hundreds of sensors, the battery, miles of wiring, and on top of that, so much of the car's brain is software. The engine control unit tweaking fuel mix, driver assist systems using algorithms, the navigation.
Software is massive now.
Massive. And all these different parts from totally different engineering worlds have to work together seamlessly, reliably, safely, efficiently. They're not designed in isolation. They're designed as interdependent parts of one big system. The brakes have to talk to the cruise control. The engine software has to work with the transmission. The whole thing relies on that synergy.
And it goes beyond just like
Yeah.
a single product, right? It can be infrastructure too.
Oh, definitely. Think about a city's transportation network. It's not just roads. It's roads, bridges, traffic lights, buses, trains, cars, all interacting. Change the timing on one traffic light downtown?
Uh-oh.
Yeah, it can create backups miles away you didn't expect. Build a new bridge. It affects traffic, sure, but also bus routes. Maybe how quickly ambulances can get places, pedestrian safety. Systems thinking helps you see those ripples, model them, try to optimize the whole network for flow and safety.
Okay. And then the classic example,
Yeah.
the one everyone mentions, the Apollo Moon program. That must have been the ultimate systems engineering challenge. The stakes couldn't be higher.
Oh, absolutely. It was just monumental. Unprecedented. It demanded systems thinking like nothing before. For Apollo, engineers had to juggle totally different but totally interconnected systems all at once.
Like what?
Well, the sheer power and precision needed for the rocket launch to even get off Earth. Then, life support keeping humans alive in space. Communication systems stretching across hundreds of thousands of miles. And the guiding software. It had to be unbelievably accurate to get to the moon, land, and come back.
Wow.
Every single piece, from the giant fuel tanks down to the tiniest sensor on the lander, had to work perfectly together for that one goal. It was a masterclass in treating the entire mission as one huge integrated system. Failure anywhere could doom the whole thing. Honestly, the coordination of all those teams and technologies was probably as big an achievement as the rocket science itself.
That's incredible.
So, yeah, by really thinking about the whole system, engineers can see how changing one part might affect others down the line. They can spot potential problems before they happen, these weird emergent behaviors that pop up from complex interactions, and make sure the final thing actually meets all the needs and constraints. If we connect this to the bigger picture, systems thinking isn't just about building parts, it's about building harmony. It changes how you fix problems too. You look beyond the broken part to the interactions around it. #tag to design trade-offs and optimization.
That makes so much sense. Okay, let's shift to something that feels really practical. Design trade-offs and optimization. We hear about engineers aiming for perfection, but, there are always limits, right? You can't have it all.
You absolutely cannot. That's like the rule number 2 of engineering, right after rule number 1, which is probably don't break the laws of physics. But yeah, this idea of trade-offs, it's absolutely fundamental in every single field. Engineering design is making decisions. It's a constant process of balancing things that often pull in opposite directions, trying to get the best possible result given all the constraints you're stuck with. It's the art of the possible, really.
So it's not about perfect, it's about best possible under the circumstances. What kind of things are engineers usually juggling? What are those competing criteria?
Oh, the list is long, but common ones. Cost is almost always huge. Money, time, resources. Then there's performance, how fast, how strong, how efficient. Safety, often non-negotiable. Durability, how long will it last. Environmental impact, increasingly critical.
And making one better usually makes another worse.
Almost always. That's the definition of a trade-off, right?
Yeah.
You sacrifice a bit of one thing to gain somewhere else. Simple example. You want to make a bridge incredibly strong and safe. Great. But that probably means using more expensive materials, more complex construction. So the cost goes way up, and it takes longer to build. The engineer's job is finding that sweet spot, meeting the safety needs without making it ridiculously expensive or impractical.
So how do they find that sweet spot? Is it just gut feeling from experience, or is there more science to it, especially when you've got like 5 different things pulling in different directions?
Oh, it's very much a science now, though experience definitely helps frame the problem. Optimizing means finding that best balance, and engineers use a lot of math, a lot of computer modeling. There's this concept called the Pareto frontier, or Pareto efficiency.
Okay.
Imagine you plot all your possible designs based on 2 things you care about, say, cost versus performance. The Pareto frontier is the line connecting all the designs where you cannot improve one thing without making the other worse.
Ah, I see. So if you're on that line.
If you're on that line, you can't make it cheaper without losing performance, and you can't boost performance without spending more. These are your best possible compromises. Which one you pick from that frontier then depends on the project's priorities. Maybe safety is paramount, or maybe getting it done fast matters most. Stakeholders get involved. It's a structured way to see the limits.
That's a really helpful way to think about it. Can you give us some more examples? Where do we see these trade-offs playing out in ways we might not expect?
Sure. Aircraft design is a great one. Think about a fighter jet versus a big passenger plane.
Totally different beasts.
Totally. The fighter is optimized for speed, agility, crazy maneuvers, but it guzzles fuel, can't fly super far, and definitely can't carry 300 people, the airliner. It deliberately gives up top speed and nimbleness for way better fuel economy, long range, and passenger comfort, plus meeting intense safety rules. Both are optimized, but for completely different goals, leading to radically different designs. Or take electrical engineering, designing an audio amplifier. Engineers often use something called negative feedback. This intentionally trades off some of the raw amplification, how much louder it makes the signal, in exchange for better bandwidth, more stability, and way less noise and distortion. So the signal might not be as loud, but it's much cleaner, much more accurate, and the amp is more reliable. It's a deliberate choice. Quality and stability over just sheer volume.
Right, because too much raw gain can make it unstable or noisy. And what about software? It seems abstract, but are there similar trade-offs there?
Oh, absolutely. A classic one in software is the space-time trade-off. Basically, do you use more computer memory space to make the program run faster, time, or the other way around?
How does that work?
Well, a program could pre-calculate a bunch of results and store them in memory. When it needs them, boom, they're right there super fast. But that uses up memory. On a phone or for huge data sets, memory might be tight.
So the alternative is?
The alternative is to recalculate those results every single time they're needed. Uses way less memory, but it's slower, uses more processing power. Another one, security versus usability. Make a system super secure with tons of passwords and checks. It can become really annoying and slow for people to actually use, make it super easy to use. You might be sacrificing some security. The engineer has to weigh those priorities for that specific app.
It's always a balance.
Always. So engineers use simulations, optimization algorithms, trade-off studies. It's not guesswork. They're trying to quantify these choices. It really is, like the old saying goes, the art of mastering the trade-offs in design. And this raises an important question. How do you decide what's best when there are so many competing factors? It forces incredible clarity about the real priorities. ###3, feedback and control systems.
That makes total sense. And it leads perfectly into our next big idea, which helps make sure those optimized systems actually work as intended. Feedback and control systems. This feels like a real cornerstone, right? It's how systems can adjust themselves, stay on target without someone constantly fiddling with them.
Absolutely a cornerstone. It's everywhere, in almost every field, and honestly, it's one of the most elegant ideas in engineering. Control theory, that's the field behind it, is all about how you regulate dynamic systems, how you make machines or processes behave the way you want them to. And the key is continuously monitoring what they're actually doing and feeding that information back to make corrections. It's about building self-correcting intelligence into the system itself.
So it's not just setting something and hoping for the best. It's this constant loop of checking and adjusting. How does that feedback loop actually work? Can you break it down?
Yeah, think of it like a little circuit. First, a controller measures the system's actual performance, maybe temperature, speed, position, whatever. That's the feedback signal.
Okay.
Then it compares that actual value to the target value, the set point you want it to be at. If there's a difference, an error, the controller calculates an adjustment to the system's inputs to try and reduce that error.
Got it. Measure, compare, adjust.
Yeah, exactly. Measure, compare, adjust, over and over. This loop lets systems automatically stabilize themselves, hold precise conditions, and even correct for unexpected disturbances like a gust of wind hitting an airplane. It's what makes so many complex things reliable.
The example everyone knows is the thermostat at home, right? How does that simple example scale up?
Precisely. The thermostat is perfect. You set it to, say, 20 degrees Celsius. That's the set point. It measures the room temp. That's the feedback. If it drops below 20, furnace on. Gets to 20, furnace off. Simple loop. But the principle scales dramatically. The same logic applies to incredibly complex systems.
Where did this idea really get formalized? Did it start with thermostats?
Oh, no, much earlier, actually. The first really famous feedback device was the centrifugal governor, used on steam engines back in the late 18th, early 19th century. James Watt is often credited.
For steam engines, what did it do?
It automatically adjusted the steam flow to keep the engine running at a steady speed, even if the workload changed. It was revolutionary for factories needing consistent power. And, fun fact, it was James Clerk Maxwell, the famous physicist, his mathematical analysis of that steam engine governor back in 1868 that really laid the groundwork for modern control theory. He showed you could mathematically predict if a feedback system would be stable or not.
Wow, from steam engines to modern theory. So where else is this absolutely critical today?
Oh, everywhere. Cars. Cruise control uses feedback to maintain speed. Engine fuel injection uses it to get the air-fuel mix just right. Anti-lock brakes, ABS, use feedback. They sense wheel lockup and pulse the brakes incredibly fast.
Right, okay.
Aerospace, autopilots, fly-by-wire systems, they're constantly using feedback from sensors to adjust the plane's control surfaces, keeping it stable and on course, even in turbulence. Chemical plants. They use feedback control constantly to regulate temperatures, pressures, flow rates, and reactors, essential for safety and efficiency.
It really sounds like control systems just completely changed the game. Enabled precision and reliability that just wasn't possible before.
Fundamentally, they transformed manufacturing, flight, communications, created whole new fields like robotics. Think about an industrial robot arm on an assembly line. It uses incredibly sophisticated feedback loops, sometimes with vision sensors or force sensors, to move with sub-millimeter precision, weld spots exactly right, over and over.
Like you said, robotics.
Exactly. Even in electronics, feedback is used in power supplies to keep voltage stable, in audio circuits to reduce distortion, even in noise-canceling headphones that create an anti-noise signal based on feedback from a microphone.
That's clever.
It is, and the theory is so powerful, our sources note it's useful wherever feedback occurs. It pops up in economics, biology, anywhere you have systems that regulate themselves. So the big idea, feedback lets engineers design systems that are self-correcting, stable, adaptive, and can hit their targets really accurately, even when things change. From your thermostat to guiding a spacecraft millions of miles away, it's the same core principle. It gives machines a kind of responsiveness, almost an intelligence. Hashtag TACOV, automation and robotics.
That's a perfect link because automation and robotics seem like the next logical step, right?
Yeah.
Taking that feedback control and using it to have machines do complex tasks with less and less human input. It feels like it's about more than just efficiency now, doesn't it? Where's this heading?
It really is the natural extension. Automation builds directly on feedback control, but aims to minimize or even eliminate the need for human intervention in a task or process. And yeah, it's incredibly broad. It uses mechanical stuff, hydraulics, pneumatics, electrical controls, electronics, and increasingly really sophisticated computer algorithms and AI. Over the last century or so, it's gone from basic machines doing simple tasks to these incredibly complex autonomous systems. It's completely changed manufacturing, infrastructure, even just daily life.
So the main drivers are obvious: efficiency, consistency. But are there other benefits, maybe less obvious ones, that push this forward?
Efficiency and consistency are definitely huge. Automated systems work fast, 247 with amazing precision. That cuts labor costs, sure, but it also reduces waste from errors, improves quality. But beyond that, automation lets us do things humans simply can't, making microchips with nanometer precision impossible for a human hand. Running the complex simulations needed for weather forecasting requires massive computing power. Automation pushes the boundaries of capability.
And this isn't brand new, right? This has been evolving for a long time.
Oh yeah, long time. You can trace it back to the Industrial Revolution, really. But a key moment people often point to is Henry Ford's moving assembly line in 1913.
Right, the Model T.
Exactly. That wasn't just about cars, it was a process innovation. Breaking down complex assembly into small, repeatable, often mechanized steps with the product moving along automatically. Fast forward to today. Modern factories are built around computer control. You've got sensors everywhere, actuators doing the work, all coordinated by PLCs, programmable logic controllers, or industrial PCs.
So robots welding cars.
Robots welding, CNC machines automatically cutting metal parts to precise shapes, conveyor belts moving things around, all orchestrated by software and feedback loops. Minimum human input needed for the core process.
And we see simpler versions at home too, right?
Totally. Power grids use complex automation to balance load and prevent blackouts. Even your washing machine runs a whole automated sequence based on the cycle you pick. Your thermostat, ATMs, they're all automated control systems we barely notice anymore.
Okay, but then there's the really cutting-edge stuff. Autonomous vehicles, robots that seem almost intelligent. What are the big engineering hurdles still left there? Getting them to work reliably in the real messy world must be tough.
It's incredibly tough. That's where the frontier is. We see amazing things already, airplanes that can basically fly themselves under autopilot using tons of sensor data and feedback, warehouses where autonomous robots just zoom around moving goods efficiently.
Like those little robot vacuums, but on a massive scale.
Exactly. And robotics as a field just keeps pushing it, combining control theory, mechanics, AI, creating drones that navigate obstacles, surgical robots that assist surgeons with incredible precision. But yeah, the hurdles are significant for true go-anywhere autonomy. Robust perception is a huge one. How do machines reliably see and understand the chaotic real world in all conditions? Rain, fog, unexpected obstacles. Safe human-robot interaction is another. How can robots work alongside people without risk? And then there's explainable AI. If an autonomous car makes a weird decision, we need to understand why for safety, trust, and fixing bugs. It's not enough for it to just work most of the time.
Yeah, you need to trust it.
You have to. And getting there requires intense collaboration across fields. Mechanical engineers design the robot bodies, the moving parts. Electrical engineers do the sensors, the power, the control circuits. Software engineers write the millions of lines of code for the logic, the AI, the interfaces. It all has to come together, the result. We're moving towards a world with smart homes, lights-out factories. It brings huge productivity gains. But yeah, it also raises big questions about jobs and society. The engineering challenge, though, is building systems that aren't just efficient, but truly safe, reliable, and adaptable in ways we're still figuring out. #TAG materials science and engineering innovations.
That's a massive challenge. Okay, let's shift to something maybe more tangible, literally. Material science and engineering innovations. It seems obvious, but everything is made of something, right?
Yeah.
How has our ability to understand and even design materials changed what's possible? It feels like we're not just finding materials anymore, we're inventing them.
We absolutely are inventing them. And you're right, it's fundamental. Every single thing engineers build, a bridge, a chip, a medical implant, is limited by the materials available. So developing new materials, that's always been a primary engine driving engineering forward. Material science and engineering is this amazing field that blends physics, chemistry, sometimes biology, to really understand matter, how it's structured, what properties it has, and then manipulate it to create materials with specific desired characteristics.
The stronger, lighter, better conductor, whatever the need is.
Exactly. Higher strength, lighter weight, better electrical conductivity, more resistance to heat or corrosion, maybe making it biocompatible so the body doesn't reject it.
And it goes right down to the atomic level, understanding the structure.
Right down to the atoms and how they bond. The core idea, sometimes called the materials paradigm, is that a material's internal structure dictates its properties. How the atoms are arranged, the crystal structure, the microscopic grain boundaries, it all matters. And here's the cool part. Engineers can change that structure. By tweaking the composition, adding tiny amounts of other elements to make an alloy, for instance, or by changing how it's processed, heating it and cooling it in specific ways, like tempering steel.
Tempering steel, right, makes it harder.
Harder and tougher, yeah. It changes the microstructure. Or doping silicon, adding specific impurities, turns it into a semiconductor, the basis for all electronics. We are literally engineering the internal architecture of materials now.
It makes sense then that we name historical ages after materials. Stone Age, Bronze Age, Iron Age. Their importance is that fundamental.
It really is. Think about steel. When we figured out how to mass-produce cheap steel in the 19th century, boom, suddenly skyscrapers were possible, long-span bridges, railroads crossing continents, heavy machinery for the Industrial Revolution. None of that was feasible with just iron or wood. Steel changed everything. Or think 20th century, the transistor, made from ultra-pure silicon crystals, carefully doped. That single materials innovation. It created the entire digital revolution. Computers, the internet, software engineering. It all flows from controlling electrons in that specific material. Even the space race in the 60s, it pushed material science like crazy. We needed new alloys, new ceramics that could handle the insane heat and stress of rockets. And those innovations eventually trickled down into everyday technologies.
So what about more recently? What are the material revolutions happening now that maybe aren't as obvious as steel or silicon?
Well, things like advanced polymers, plastics have been huge, synthetic rubbers, better semiconductors, biomaterials for medicine, but a really big one now is high-performance composites.
Like carbon fiber.
Exactly. Carbon fibers embedded in polymer resins, they're incredibly strong, but also incredibly light. That's revolutionized aerospace. The Boeing 787 Dreamliner is a famous example. Its airframe is mostly composite, saves huge amounts of weight, which means huge fuel savings. That's a massive design trade-off enabled by the material. We also see composites in cars, sporting goods. Everywhere, lightness and strength matter. Polymers have given us things like Kevlar for body armor, flexible materials for electronics you can bend, and the real frontier now, nanomaterials.
Tiny stuff.
Like manipulating matter almost atom by atom. This lets you create materials with totally unique, exceptional properties. Think nanostructured electrodes for batteries that charge way faster and hold more energy, quantum dots for super vivid TV screens, maybe even material that can heal themselves if they get microscopic cracks. It's moving towards materials with almost programmed behaviors.
Wow. It really sounds like material science is the ultimate interdisciplinary field. It touches everything.
It absolutely is. It's the connective tissue. Mechanical engineers need materials knowledge for structures, engines. Electrical engineers need it for chips, wiring, magnets. Chemical engineers need it for catalysts, polymers. Biomedical engineers rely on it for implants, drug delivery systems that work safely inside the body. The big idea is simple but profound. Better materials enable better technology. Full stop. Mastering how to make and shape materials unlocks new capabilities across the board. Every time we get a new breakthrough material, silicon, carbon fiber, graphene, whatever's next, it just expands the horizons of what engineers in all fields can actually build. Hashtag, CTAGs, sustainable energy and renewable systems.
That's a great link to our next big idea, which is hugely important right now. Sustainable energy and renewable systems. I mean, this isn't just an engineering thing. It's a global challenge affecting everyone, right? Climate change, resources.
Absolutely. This has become one of the dominant drivers of engineering innovation in the last few decades. As we face climate change, finite fossil fuels, engineers are right at the forefront, developing, optimizing, deploying technologies to get energy in cleaner, renewable ways. And it's not just one type of engineer. It takes a huge, multidisciplinary effort.
Like who?
Well, energy engineers specifically, obviously, but also electrical engineers designing power grids and conversion systems, mechanical engineers working on turbines and engines, material scientists developing better solar cells or battery materials, even civil and environmental engineers dealing with the infrastructure and the ecological impacts.
So the focus is optimizing the whole energy picture and dealing with these huge global challenges. What are the biggest engineering hurdles still? Making renewables reliable and scalable must be tough.
It is. Modern energy engineering is about optimizing entire systems, developing those renewable techs, solar, wind, hydro, geothermal, biomass, and also, crucially, improving energy efficiency. So we just use less energy overall. But yeah, the hurdles are real. Solar and wind are intermittent, right? The sun sets, the wind dies down.
But the grid needs power 247.
Exactly. So a massive engineering challenge is energy storage. We need better, cheaper, large-scale batteries, lithium-ion, maybe newer chemistries, or things like pumped hydro storage, maybe using hydrogen, something to smooth out those peaks and valleys in supply. And we need smarter grids.
What are grids?
Yeah, using sensors, software, controls feedback loops again, to manage the flow of power from all these distributed sources much more efficiently, predicting supply and demand, rerouting power, making the grid more resilient.
So what are some of the key innovations that have made renewables actually viable competitors now?
Solar PV photovoltaic panels are a huge success story. They turn sunlight straight into electricity using semiconductors. Thanks to relentless work in materials science and electrical engineering, their efficiency has shot up and the cost has just plummeted. That's made solar power really competitive in many places.
And wind turbines too, right? They're massive now.
Huge. Modern wind turbines are incredible feats of engineering. Aerodynamics from mechanical and aerospace, structural design from civil, sophisticated control systems. They're constantly adjusting pitch to capture the most wind. And yeah, the scale is amazing. Offshore turbines now have rotor diameters bigger than 2 football fields, generating megawatts of power each. And big solar farms can cover huge areas.
You mentioned a specific example, Nellis Air Force Base.
Yeah, that was an early large-scale example in the U.S., a big 140-acre solar PV farm generating about 15 megawatts for the base. It really demonstrated that utility-scale solar was practical, that you could integrate large amounts of clean energy into the grid. It was a proof of concept back then.
Okay, so generating the power is one thing, but making it work for the grid 24/7, dealing with that intermittency. That sounds like the really tricky part engineers are wrestling with now.
It's absolutely critical. Beyond just making the panels or turbines, engineers are focused on making renewables practical. Energy storage is key, like we said. Smart grids are key. And also, just using energy more efficiently makes the transition easier. Things like LED lighting, cutting electricity used dramatically, electric vehicles replacing gasoline cars. It all helps reduce the total load the grid has to handle. Energy engineering is really its own specialty now, pulling together knowledge from thermodynamics, electrical grids, materials, environmental science. Look at an electric vehicle. It's a perfect example of this synergy.
How so?
Mechanical engineers do the drivetrain, the aerodynamics. Electrical engineers handle the battery management system, the motors, the power electronics. Chemical engineers work on the battery chemistry itself, getting more range, faster charging. Software engineers write the code that manages everything, optimizing how energy is used, all working together for sustainable transport.
That's a great illustration. And you see that same complexity in, say, building a giant offshore wind farm.
Oh, absolutely. For an offshore wind farm, you need civil engineers designing foundations that can withstand ocean forces. Mechanical engineers for the turbines themselves, making them reliable in salty, windy conditions. Electrical engineers figuring out how to get all that power back to shore through massive underwater cables. Environmental engineers studying the impact on marine life. It's a huge coordinated effort. The big picture goal here, transitioning our whole energy system off fossil fuels towards renewables, reducing carbon, creating a sustainable economy. If we connect this to the bigger picture, this is really engineering tackling one of the most urgent global challenges we face. It's systems thinking on a planetary scale, optimizing how we generate, distribute, and use energy for the long haul. #####7.
Failure analysis and continuous improvement. That's a powerful goal. Okay, last big idea, and it feels a bit different. Learning from failures. It sounds almost counterintuitive, like engineers should avoid failure at all costs. But you're saying it's actually crucial. How does looking at what went wrong help push things forward and build trust?
It's absolutely crucial. It's like the ultimate feedback loop for the entire profession. Look, engineers work incredibly hard to make things reliable and safe. And mostly, they succeed spectacularly. But failures happen, sometimes small, sometimes devastating. The big idea here is that these aren't just mistakes to be swept under the rug. They are incredibly valuable lessons. They often become the catalyst for huge improvements. There's a whole field of failure analysis or forensic engineering dedicated just to figuring out why something failed and how to make sure it never happens again.
So it's like engineering detective work, a systematic investigation.
Exactly like detective work. It's systematic, often painstaking. Forensic engineers collect evidence from the failure site. They examine the broken parts, sometimes under powerful microscopes, looking for clues. Was it a design flaw? A bad calculation?
Or maybe the material itself.
Yeah, a hidden defect in the material, corrosion. Or did the system get overloaded somehow? Was there human error in how it was operated or maintained? The goal is always to find the root cause. Not just the immediate symptom, but the fundamental reason it failed. And then, crucially, use that knowledge to change future designs, change manufacturing processes, change operating procedures. It's vital for improving safety, for figuring out liability, and for maintaining public trust. There's that grim saying in engineering, many standards are written in blood.
Wow. Meaning they came directly from learning from tragedies.
Often, yes. Standards were updated, designs were changed because a failure caused harm, and engineers were determined it wouldn't happen again.
Can you give some landmark examples, failures that really became turning points?
Oh, there are many famous ones. The Tacoma Narrows Bridge collapse in 1940, Galloping Gertie.
The one that twisted itself apart in the wind.
That's the one. Engineers didn't fully understand aerodynamic forces on bridges like that back then. Its collapse taught tragic but invaluable lessons about resonance and aeroelasticity. It led to totally new ways of designing long bridges, making them much stiffer, letting wind pass through. It changed bridge engineering forever. Or the Challenger space shuttle disaster in '86, the O-ring failure in cold weather.
I remember that.
It led to massive changes at NASA, better materials for critical parts, totally revamped risk analysis, and a huge cultural shift towards prioritizing safety and listening to warnings. In chemical engineering, big industrial accidents like Bhopal in India or the Deepwater Horizon oil spill, they led to much stricter safety rules, more redundancy, better emergency systems, and process plants.
And wasn't there something with early jetliners and square windows? The comet crashes.
Yes, the de Havilland Comet.
Yeah.
Early jetliner, very advanced for its time, but several broke up mysteriously in midair. Investigators eventually figured out that metal fatigue cracks were starting at the sharp corners of the square windows, growing with each pressurization cycle until catastrophic failure.
Because of the shape of the window.
The stress concentrated at the sharp corners. That discovery led directly to rounded windows on all airplanes ever since. And it pushed the whole field of fatigue testing and designing for metal fatigue. It led to reliability engineering, designing with safety factors, planning maintenance to catch problems early. And engineers don't just wait for failures. They use methods like FAA failure mode and effects analysis during design. They try to anticipate what could go wrong and build in safeguards from the start. When failures do happen, the investigation is always interdisciplinary. Material scientists looking at cracks, mechanical engineers analyzing stresses, electrical engineers checking circuits, software engineers hunting for bugs. In a plane crash investigation, they'll analyze metal fragments, black box data, software logs, run simulations, all to piece together exactly what happened.
So the outcome is safer designs, better standards, better procedures.
Exactly. Failure analysis saves money, saves lives, saves resources by preventing repeats. It leads to better materials, updated building codes after disasters, better checklists, and inspections.
So it really is about this constant cycle of improvement. Being honest about mistakes and learning from them is baked into the process.
It is. It reflects this core engineering ethos. Continuous improvement. Every setback is a chance to learn, to refine. And over time, this honest, rigorous process has made engineered things incredibly safe and reliable, from bridges that withstand earthquakes to software that fails gracefully instead of crashing the whole system. It shows that engineering moves forward not just through brilliant invention, but also through the meticulous, sometimes painful examination of what went wrong. It's about constantly getting better. Hashtag, tag, outro.
Wow, what an incredible tour through these big ideas in engineering. It's really clear how they all weave together, isn't it? Systems thinking, optimization, feedback, automation, materials, sustainability, learning from failure. They really are the common threads, the shared mindset behind it all.
Absolutely. Doesn't matter if you're building a bridge or a microchip, a power grid, or software. These core principles apply. They guide engineers to see the whole picture, to balance those competing needs, use feedback for control, pick the right materials, automate where it makes sense, aim for sustainability, and always learn from mistakes. They unify the practice and drive it forward. Understanding these ideas really gives you insight into how engineers think, that blend of analytical rigor and creativity.
So, as you, our listeners, go about your day, think about these ideas. Engineering, really, it's about using science creatively, responsibly, to solve problems and hopefully build a better world. It's systematic, it's innovative, it's focused on making things work. It's been that way since the first person invented a lever or a wheel. So look around. What other examples can you spot where engineers have masterfully handled trade-offs, built in clever feedback loops, or turned a failure into a stronger design? Thank you so much for joining us on this deep dive into the big ideas shaping our world. We hope you'll keep exploring.